Suppose ax equals b is an inconsistent linear system. Then there's no vector x that makes this equation true. But we could try to find a vector x that makes this equation as close to being true as possible. That's called a least squares solution. In this video, we'll go over least squares solutions and how to find them with the techniques of linear algebra. Most of our discussion will be in the context of Rn, but a lot of this content, including a theorem that we'll be proving, applies to inner product spaces in general. We'll also go over normal equations and how they can be used to find least squares solutions, and we will do two full examples of finding a least squares solution. One example with a unique solution, and one example with infinitely many. This video has chapters, so you can skip around as you please. For an example of an inconsistent linear system, we can consider this. These are 3 points that don't all lie on the same line. Each of these equations is of the form y equals the y-intercept plus the x-coordinate times the slope. You can see the x-coordinates there, and you can see the y-coordinates there on the right side. So if these points did all lie on a single line, we would be able to find some y-intercept c0 and some slope c1 that made all of these equations true. But since the 3 points are not collinear, this system of equations, in fact, is not consistent. We will not be able to find a line that passes through all 3 of these points. But we may still want to find a line that comes as close as possible to doing so. This is a really important thing to be able to do, because in the real world, it's never the case that we're perfectly able to fit a curve or a line to a set of data points. There's just too much going on. There's so many factors in the real world that could affect your data. There's random noise, there's measurement error, you're just never gonna get a perfect fit. But it could still be the case that the underlying relationship observable in the data is really a line, or some other curve that you might try to model it with. As a result, we're stuck with the burden of doing some serious mathematics to try to find the curve or the line that best represents that relationship we're observing. In this case, trying to find the line that best fits the points. At the end of this video, you can come back to this problem and use the techniques we're going to cover to find the equation for this line. But now there's some important terminology we need to cover. Putting this problem into the context of matrices, we would have this coefficient matrix A, those are the coefficients of C0, the coefficients of C1, and then we'd have this vector of constants B, and this solution vector X. But of course, the system's inconsistent, so we know there is no x such that ax is equal to b. But the idea is that we can look for an x that minimizes the error. No matter what vector x we find, a times x is not going to equal b. There's going to be some distance between them, the norm of b minus ax. But we are trying to minimize this. Now, if such a minimizing vector x exists, it's called a least squares solution of ax equals b. It doesn't make the equation true, but it does minimize the error, and we'll talk about where this term least squares comes from in a minute. Now, that distance vector, b minus ax, whose norm we are minimizing, that's called the least squares error vector, and its norm that we're minimizing is called the least squares error. To see where this term least squares comes from, we need only consider the error vector b minus ax. b, of course, is a column vector, and ax is also a column vector. If we subtract them, we get another column vector whose entries are individual errors. In the context of this problem, if we had a value for C0 and C1 that we thought minimized the errors, we could plug those in, and the difference between the left side and the right side, that's what we would have in this error vector, all of those individual errors from each equation. Now, when we minimize the norm of this error vector, it just so happens that also minimizes the square of the norm of the error vector. But the square of the norm, looks like this. Of course, the norm of the error vector would just be the square root of e1 squared plus e2 squared, and so on. So if we square that, what we get is this, that's just without the square root. So when we minimize this error, it just so happens that we're also minimizing the sum of the squares of those individual errors. We're finding the least squares. Now again, I want to emphasize that the matrix A is known. What we're looking for, the least squares solution, is this vector x that when we multiply by A, will give us a vector closest to B. In a minute, I'm going to show you a picture that makes it abundantly clear exactly what the vector A times x that's closest to B looks like. We'll see exactly what it is, but it's really important that you understand a key detail first. This shouldn't be new information, but let's just make sure it's clear because it's really important. A times x is a linear combination of the columns of A. And so by definition, A times x is in the column space of A. No matter what our least squares solution vector x is, hopefully you can imagine multiplying A by x as we see here, and how that would be a linear combination of A's columns. For example, you can see how C0 is going to hit every single entry in the first column if we were to do this matrix multiplication. C0 hits every entry in the first column. Similarly, C1 would hit every entry in the second column of A. And so again, hopefully it's clear that A times x is a linear combination of A's columns, and so is in the column space of A. This means that in looking for a least squares solution x hat that makes the product ax hat as close to B as possible, that's like looking for a vector ax hat that's in the column space of A that's closest to B. And this picture tells us exactly what ax hat is going to have to look like. So the gray parallelogram, that's the column space of A. Every single vector that we take in this space is a linear combination of the columns of A. It's some vector of the form ax. Then we also have this vector B, which lies outside of the column space of A. So B isn't in the column space. There's no vector in the column space that's equal to B, but what we're trying to find is a vector in the column space that's closest to this vector B. Most of the vectors in the column space have a great distance from the vector B. Some are closer than others, but we're looking for the vector which is closest. This vector ax clearly is not the closest to B. That's all the way out here. We have to go backwards and up quite a ways to get back to B. This vector ax is far from B. It's not a very good approximation. If we want a vector that's as close to B as possible, but it has to be in the column space of A, it makes sense that we would want to go from B directly down to the column space. We don't want any unnecessary distance. We want to get directly down to the column space from B. In other words, we need to project B onto the column space, and it's precisely that vector which is closest to B. I'm calling this ax hat just so you can see that this vector x hat is fixed, whereas ax is just representing an arbitrary vector from the column space. X hat, on the other hand, is specifically a vector that makes ax hat equal to the projection of B onto the column space of A. The vector in the column space of A that is closest to B is just the shadow cast by B on the column space. And what makes this geometric intuition so beautiful is that it doesn't just apply in R cubed, nor only in Rn, but in inner product spaces in general. If we have a vector that lies outside of a subspace of some inner product space, the best approximation to that vector that lies in the subspace is the projection of the vector into the subspace. This is called the best approximation theorem, and we'll do a quick proof before actually getting into some problems. If W is a finite dimensional subspace of an inner product space V, and if B is a vector from that inner product space, then the projection of B onto the subspace W is the best approximation to the vector B from that subspace, meaning that the distance between B and its projection on W is less than or equal to the distance between B and any other vector from W. The proof relies on the generalized Pythagorean theorem for inner product spaces. I'll leave a link in the description to my lesson proving that. But for our proof, we're going to take an arbitrary vector from the subspace W, and then we're going to consider this error vector, B minus W. Then we just add 0, but in a very useful way. We subtract the projection of B on W, and we add the projection of B on W. Now what we have here on the left is B minus its projection on W, and that is the component of B that's orthogonal to W. Hence, it's an element of the orthogonal complement of W. On the other hand, the projection of B on W minus W is a difference of two vectors that are both in the subspace W. B's projection on W is obviously in W, and W is obviously in W. So this difference of vectors must also be an element of the subspace W. Since this vector is in the orthogonal complement of W, and this vector is in W, they must be orthogonal. Their inner product is 0. So we can apply the Pythagorean theorem. The Pythagorean theorem tells us that if one vector is equal to the sum of two other vectors, the square of the norm of that one vector is equal to the sum of the squares of the norms of the other two vectors. So in particular, we have the norm of B minus W squared must equal the sum of the squares of the norms of these two orthogonal vectors. Then this squared norm on the right is certainly non-negative. So if we got rid of it, we would either not change the right side if it happens to equal 0, or we would reduce the right side in the more likely case that it is a positive number. Hence, if we get rid of this term on the right, this non-negative term, then we have that this must be less than or equal to this. And you see that there. This guy needs to have stuff added to it in order to get this equality. So this guy is less than or equal to the squared norm of B minus W. But from that inequality, taking square roots on both sides, we get the desired result. The norm of B minus the projection of B on W is less than or equal to the norm of B minus W. And it's only because norms are positive that we can go from here to here. For example, we know that 2 squared is less than or equal to negative 5 squared, but that doesn't mean that 2 is less than or equal to negative 5. When there's negatives at play, jumping from something like this to this is not so straightforward, but it's because norms are positive, we don't have to worry about that. But that establishes the theorem. So the best approximation to the vector B from the subspace W is B's projection on W. Again, the really neat thing about this theorem is it applies in inner product spaces in general. But let's take this back to the systems of linear equations we were thinking about in Rn. Applying this theorem to that situation, we'd have Rn as our vector space, and W, the subspace, would be the column space of a matrix A. Then the theorem tells us that the best approximation to B from the column space of A is the projection of B on the column space of A. And since every vector in the column space of A has the form A times X, we know there exists some vector, say x hat, so that A times x hat is that projection of B on the column space. Hence, we know that there is a least squares solution. Now, that least squares solution might not actually be unique, but certainly the minimum error is. If it was possible to find some other vector x so that AX gave us even less error, well, that would ruin the whole point. The whole point is minimizing the error, but there could be multiple vectors that do that. Like I said, in the problems we go through, we'll see a unique solution and an example with infinitely many solutions. All right, so how do we actually find a least squares solution? Well, we've figured it out, right? A times X has to equal the projection of B on W, which is the column space of A. So we just need to find that projection and then solve this system for X. Well, not so fast. We could do it this way, but if we do a little bit of math first, we'll see that we can actually avoid having to calculate that projection. So check this out. We're going to negate both sides of this equation and add b to both sides. Hence, we have b minus ax equals b minus the projection of b on w. Now, b minus the projection of b on w, of course, that is the component of b that is orthogonal to w. So it's an element of the orthogonal complement of w. But remember, w is the column space. So that means it's orthogonal to the column space. But that means that it's in the null space of A transpose. So what happens if we multiply both sides of this equation on the left by A transpose? Well, on the left, of course, we'd have A transpose times B minus AX. But on the right, we have A transpose times this vector, which, because it's orthogonal to the column space, must be in the null space of A transpose. And remember, that's because, as we've previously proven, the column space of a matrix is orthogonal to the null space of its transpose. Now, this means that A transpose times this, since that's in the null space of A transpose, this product is just equal to 0. So we have that A transpose times B minus AX equals 0. Then, distributing A transpose and adding A transpose AX to both sides, we arrive at what's called the normal equation associated with the system AX equals B. And it looks like that. A transpose AX equals A transpose B. So there's no projection calculation necessary. All we need to do is some transpose, some matrix multiplication, and then just solve this system for X. Any solution of this system is going to be a least squares solution. So then we've established this result. For every linear system, AX equals B, the associated normal system, A transpose AX equals A transpose B, is consistent, and its solutions are precisely the least squares solutions of the system AX equals B. Furthermore, if x hat is any least squares solution of AX equals B, then AX hat must equal the projection of B onto the column space of A. Now, how do we know this system that gets us those least squares solutions, how do we know that's consistent? Well, remember, this equation came from this one. And this equation obviously has a solution, because the equation is AX equals the projection of B on W. W is the column space of A, and every vector in the column space of A has this form. So there has to be some vector x, so that AX is that projection. Since this equation always has a solution, this one does as well. And as we proved, that solution is going to be the least squares solution, because the projection of B on W is the closest we can get to B from a vector that's in W. All right, let's try it. We're going to find a least squares solution, the least squares error vector, and the least squares error of this linear system. This system is not consistent. There's no solution vector that makes it true, but we can try to find one that makes it as close to true as possible. So what we're looking for is a least squares solution of the system AX equals B, where A is this coefficient matrix, the coefficients of x1 are in column 1, coefficients of x2 in column 2, and our constant vector, of course, is B. We know to find the least squares solution, we can use the normal equation seen here. A transpose A, we can calculate easily. This is A transpose, this is A, and the matrix multiplication is straightforward. We get that. On the other side, A transpose times B, let's do that as well. Here again is A transpose. Here's our column vector B. The matrix multiplication is straightforward, and we arrive at that column. So finally, this whole problem comes down to solving this system. A transpose A, which is there, times that vector x equals A transpose times B, which we see there. We can then represent this system with an augmented matrix, coefficients on the left and constants on the right, and then perform Gauss-Jordan elimination, and you can verify, if you want, that we arrive here, telling us the least squares solution. x1 equals negative 116 over 341, and x2 equals 380 over 341. Then the least squares error vector is b, the vector we're trying to approximate, minus ax, our best approximation. This is b, this is a, this is the least squares solution vector that we just found. Doing the multiplication, a times x gets us here, and then b minus a times x is this. That's the least squares error vector. The norm of this vector is what we have minimized by finding this least squares solution. Any other vector we could find would also have some error vector, and every one of those would be bigger than this one. The least squares error is the norm of this least squares error vector, and that's about 0.27077. Note in this example that the least squares solution was unique. We had one value for x1 and one value for x2. So that's how this process is done with the normal equation. Let's go through another example where we will have infinitely many solutions. So we're just doing all the same stuff again. We're going to find all least squares solutions, the least squares error vector, and the least squares error of the system. Here is our system. It is inconsistent, but we can try to find the best solution possible. We seek a least squares solution of ax equals b, where our coefficient matrix A is seen here, and b, our constant vector, is there. We need the normal equation, A transpose ax equals A transpose b. This is A, so this is A transpose. A transpose times A, then, is this matrix here. A transpose times B, we see here, the matrix multiplication is straightforward. Then the normal equation, A transpose AX equals A transpose B, can be written with matrices like this, and then represented as an augmented matrix like this, and then you can perform Gauss-Jordan elimination and verify that we would get this reduced row echelon form matrix. We see that there's no leading entry in column 2, and so in this case, x2 is actually a free variable. Let's assign it to the arbitrary parameter t. From row 1, we have that x1 equals 6/7 minus 2t. And so we see there are infinitely many least squares solutions. But despite the fact there are infinitely many least squares solutions, the error vector and its norm are unique. b minus ax is seen here. That's b, that's a, and that's the least squares solution vector that we just found. Now if you do this multiplication, you see that the t's actually go away. Doing this row with this column, we would end up having negative 4t plus 4t. Going on to the next entry and thinking about the t's, we would have negative 6t plus 6t, and so on. You can see all the t's cancel out, and we end up with a unique least squares error vector, and of course a unique norm as well. The least squares error is about 1.6475. Any vector x that's not of this form would lead to an approximation ax that also has some error, and they would all have more error than this. So that's how to find a least squares solution using the normal equation and the techniques of linear algebra. We also took a look at the best approximation theorem, addressing this problem of approximations in inner product spaces in general, and we'll certainly be using this outside of Rn later in this course. I hope this was helpful for both your intuition and understanding of the solutions of these sorts of problems, and why we would need to solve a problem like this in the first place. Again, the idea is that models, like linear models, can capture some real truth, but the real world is just so messy that real data is never going to fit a model perfectly. Let me know in the comments if you have any questions, and be sure to check out my linear algebra course and linear algebra exercises playlists in the description for more. If you find my videos helpful, please consider supporting what I do by joining Wrath of Math as a channel member. You can get early and exclusive access to videos and extra practice, and if you join at the premium tier or above, you can access the lecture notes that are used in the course. Thanks for watching.
Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about. Stressed out, honey, I've been stressed out lately. Don't know what's what, don't know what I'm stressed about. Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed